I think we can start. Yeah, I will share my screen. Okay, so just a brief introduction on what I'm going to do today. So as you know, in version 3, we also moved the external solver library, which is basically what you can find in the installation folder of STKO. For example, you go here, program files, STKO, and then you have a folder called external solvers. And this one is full of Python files, okay? And all these Python files are used for definitions, physical properties, element properties, conditions, and analysis steps. So you have one of them for each component inside STKO. And it is used to connect STKO with OpenSys. Now this one is available on Github. Like, for example, let me go here. Repository view on Github. Okay, and I will share the link with you. I can share the link with you for the ASDEA software GitHub webpage. I'll share it in the chat. Okay, so this one is the link for GitHub. You can go here and you will be able to visualize only this first repository, okay? Instead, I have many others because some of them are private, but this repository, external solvers STKO, is public, okay? So you can work with it. You can see what's inside and you can work with it. So today we'll try to explain you how it works, just the basic ideas, okay? Now, to understand how to work also with GitHub, you need some experience, okay? So I don't have time now to explain how GitHub works, but there are some nice tutorials. For example, if you want to learn how to use GitHub, you can directly go on the OpenSys GitHub, and they also selected, because they're also using GitHub for this, they also selected a couple of webinars, a couple of documentation here to tell people how to start working with forking a repository and doing all the changes and asking the maintainers of this repository to accept your own changes, okay? So you can work, you can see this documentation here and this one, okay? So if you want, you can go on the OpenSys GitHub, and then here you can find some suggestion and some documentation, okay? And I will post this one also on the chat. Okay, so the basic idea is that when you have a repository like this, you cannot directly, as it is written also here in OpenSys, you don't have the right to directly write inside this repository. What you can do is to create a fork of this repository. It means your own version of this repository. And you can do the changes in your own version, and then you can do a pull request. A pull request is a kind of request to the maintainers, okay, to add your own stuff. And they will visualize it, okay? You explain why you want to do this change, they will visualize it. And if all your changes do not break anything on the code, they will probably merge it to inside the main repository, okay? So for example, here in OpenSys, you can see many forks. What you can do, for example, is to go here, you can create your own fork, okay? Now in my case, for example, I have already a fork of OpenSys because I'm also contributing to OpenSys. But if I want to create, for example, a new fork for the ASDEA soft, I can go here, okay? So this is the first step you have to do. You have to install, if you want, the GitHub desktop, which is a nice GUI for GitHub. And the first thing you have to learn a little bit about GitHub, okay? So now I will show you how it works for the external solver and STKO. Now, the idea is that with Rafael, which is here now, we decided to create a plugin inside STKO for modeling the passage of a train, okay? And what we want to do is basically, let me do a sketch. But what we want to do is to model the passage of a train, not just like a moving load, but also as a moving mass and a moving spring, like with the spring and damping coefficient. So something more complicated. And the idea would be, for example, imagine you have a plate, okay, something like this, which is discretized in many finite elements, like shells, for example. And then you have a point here, okay, which represent your train, for example, where basically you have a vertical force, which is the weight of the train here. You have a mass, and possibly you have a damping, okay, and the stiffness of the train as well, for example. So what we want to do is basically to create an automation for creating a node, creating the projection of this node onto this plane here, create a spring and a dashpot here. So an entire system that has a load, a mass, a stiffness, a spring. And the idea would be to let the user define a trajectory, okay, for the passage of the train. And then the idea would be, for example, at a certain time step, this node would be, for example, here. What we want to do is to compute the projection of this node, and then to understand where these nodes, what is the element this node falls into. For example, in this case, it will be this element. And then we want to apply a constraint, a particular constraint, such that this node will move as a weighted average of the displacement of the other nodes. Well, this one basically translates in transferring this force here, which is W, on the other nodes, okay? And these projections are proportional to the distances of the projected node from the other nodes. For example, if this node is actually here, the entire load goes here. If it is at the centroid, it will be divided by 4, and so on. Now, creating this entire script, it will take a lot of time, so we cannot do it completely in this webinar. What I will do is I will start by creating an automation that creates this kind of constraint, okay? So you will understand what is this constraint, what is the new element we added to OpenSeas for creating this constraint. And so this is the first building block that we will use in future webinars for creating this entire automation, okay? So for this time, I will work only on adding a new element to STKO when you have a new element in OpenSeas, okay? So the basic idea is that whenever you or someone else add a new component to OpenSeas and STKO is not interfaced already with that new element, you can create a new Python script that tells STKO how to create a GUI for it and how to write the OpenSeas comment, okay? So this is the first step we will try to do today. Okay, so I create all drawings. Okay, so the first thing that I will do is to explain you first how this new element works. Now, this new element is not yet in OpenSeas. I will create a pull request in a couple of days, but the element is called ASD constraint equation element. It's just a very generic element where basically the user can define the equation that relates one degree of freedom to another, okay? I will give a simple example. Okay, so I will start with a simple file that you can find here, test constraint equation element. So now imagine you have OpenSeas, you develop this new element or this new material, this new component in general, but the STKO is not aware of this new component. So you need to write a Python code for STKO, okay? But the first thing that we're going to do is try to understand how it works without STKO, okay? So let me start with a basic example without this node and without this stuff. It's not important. And also, I'm going to comment this. I will comment this one. Okay, so this is fine, and I need to comment this one. Okay, so now basically this example is very simple. Okay, it's a one DOF problem. Okay, so you have one dimension, one single DOF. Okay, So the nodes, you have here just two nodes, one placed at coordinate 0, one placed at coordinate L, which is the length of this truss, for example. Now I made everything equal to 1 to make a normalized example, but you can change the values, okay? And then I place a uniaxial material here with this young modulus, and I create a truss element, okay, with this area that connects node 1 to node 2. So the first node is fixed, so the only degree of freedom which is free is the second off here. I apply a load equal to 1 to the second off, okay? And then I solve it, and I want to see the displacement at the first node and at the second node. Now, of course, I will have a displacement of 1 because everything is normalized. So I have a stiffness of 1, a force of 1, I will have a displacement equal to 1. And then I will show you what happens with this new constraint. So let me go here. I open a command prompt. And what I'm going to do is to use my own version of OpenSys. And I want to run this file, okay? So the output is going to be, I need to save it, of course. Otherwise, I'm running the other, okay? So I run this one. And of course, I have displacement at node 1, 0, displacement at node 2 equal to 1, okay? So this is perfectly simple. It's a simple spring. Now, what I want to do is to add another node, which is node 3, which is placed in between the two, okay? So its position will be L divided by 2. Now, if I keep the model as it is, this node is not connected to anything. So my system will be singular. Now, let's see. So I clear this one and I run it again. I should see an error somewhere. Oh, I didn't save it. Okay, now it's saved. Clear. Okay. And I will see, okay, now the system is singular at the second row here. Okay, this makes perfectly sense because now I have an extra node which is not connected to the other nodes with any element. So this degree of freedom is actually singular. So what I want to do is to constrain the displacement of node number 3 to be the weighted average of the displacement of the other node. So this one is the equation that I want to apply. Ux of node 3 should be equal to 0.5, the displacement of node 1, plus 0.5 displacement of node 2. Okay. So what I can do is to create a constraint equation element, which is this one. This is the new element we added. So first of all, you may ask, if you are trying to add a multi-point constraint, why are you adding an element instead of a constraint? The problem is that in OpenSys, you cannot add a constraint which is so generic, okay? Because the only constraint that you can apply in OpenSys is a constraint where you have many slave nodes, but only one master node, like rigid links, equal DOF, rigid diaphragms. So the typical multi-point constraints that we find in structural analysis. But the more generic constraint equation cannot be applied through the real constraints in OpenSys. So what I decided to do is to create an element that applies a constraint using the penalty method. In fact, when you add a constraint using the penalty method, what you're actually doing is to add an element with, it's like to adding many springs inside your model, okay? So how this element works. So you have, of course, the keyword element, the name of the element, the tag of this element. Of course, it should not overlap with the existing elements. Then you need to specify a stiffness parameter, which is a stiffness that represents a penalty parameter, okay? So I've been talking about penalty parameters in many webinars. The concept is always the same. The penalty, okay, so the penalty parameter should be a number that should be sufficiently high to impose the constraint, but not so high to make the entire system Hill condition. So the typical idea is to evaluate the typical stiffness of your model. Now, in this case, the stiffness will be 1 because I have E times A over L, and it is 1, 1, 1. Okay, so my typical stiffness will be 1. Then I need to compute the order of magnitude of my stiffness and the order of magnitude can be computed like this, so a round of log 10 of the typical stiffness of my model. Then I add 8 digits to this order of magnitude, and I have the power of my penalty number. So my penalty number will be 10 to the power of this number, okay? And then I will print it. Of course, I will see 1 to the power of 8, okay? Now, once I define this penalty parameter, I have to specify the constraint node and the constraint DOF, and this is mandatory. And then optionally, I can have a list of triplets, okay, where each triplet has the retained node, the retained DOF, and the retained factor for the node 1, and then the same thing for the node 2, and so on. Now, in my case, I want to apply this equation. So this one is the constraint node. Node number 3 in degrees of freedom x. So the node ID, which is this one, is 3, and the constraint DOF is 1. Okay. Then the first retained node is node number 1, okay, which is the fixed node. The DOF is 1, and I want to multiply it by 0.5 plus node 2, DOF 1, and the factor will be 0.5. Okay, so this one is basically saying the displacement of node 3 should be exactly 1/2 of this one plus 1/2 of the other. Okay, so exactly in the middle. Okay, so let's see what happens now. So if I do this, now my model should not be singular anymore. And I should see a displacement of 0, 1, and for node 3, I will see a displacement of 0.5. Okay. We have someone else. Okay, here we are. So the concept is very simple. With this constraint equation, you can do a lot of things. Now, this one is very, very simple. I'm just doing the a weighted average of the displacement, but you can use this kind of constraint for much more complicated things. For example, I don't know, if you want to do a degree of freedom, something like this. Imagine you have a beam in this direction and you want to apply a roller which in a skew direction, for example. You can do the same thing, because this one will be the constraint node and the retained node at the same time. So you can say that the x displacement at this node should be connected to the y displacement at this node using coefficient related to the cosine and sine of the angle. So you can do a lot of things. By the way, this is the same approach I use for the embedded node element. Okay, in the embedded node element, I use the exactly same approach, but I do not let the user input the equation. I directly wrote the equation inside OpenSys. Instead, this one is a much more general kind of constraint that can be used in many different scenarios. And in this case, we are going to use it for attaching a node on an element. Okay. So this one is a very simple example. Now we have this new element in OpenSys, but this new element is not in STKO. Okay. So imagine now we'll run my own developed version of STKO, because of course I'm going to develop this new element. And I will show you that even if this new element is inside OpenSys, it is not available in STKO version 3.0. Okay. So for example, it's not inside elements here, and it is not inside conditions. But for example, you can see that inside conditions, I have under constraint multipoint. Oops, not here. Sorry, I need to. Well, now it is available because I already did this test. Now I go back to my main branch, switch branch. Okay, so this one is the default branch, and I don't have this constraint anymore. So let me open STKO again. And I will show you step by step how you can add it. Of course, I already did it. So I have my, what is it? I have my code here. So I can go faster. I can just let me, okay, it's fine. Okay. So the first thing that you have to do when you want to apply a new element inside STKO is to, you have to create your own fork of the external solver. which is here. You go here on fork and you create your own fork. Okay. Well, once you have the fork, it will ask you to open it with GitHub desktop. Of course, you have to decide in which location you want to have your fork. In my case, it is inside. What is it? It is here in develop STKO external solvers. Okay. Now, as you can see here, what I want to do is to apply this element as a constraint. Okay, so for the end user in STKO, this one will not be an element; it will be a constraint, as I did for the embedded node element. So I will place a file here. Okay, so let me do this first thing. So as you can see now in condition, if I go here, constraint MP, I only have ASD embedded node element, but I don't have the ASD constraint equation element. Okay, so the first thing that I'm going to do is to close STKO, and now I want to add a new file. This new file is going to be new. It is called ASD constraint equation element .py. Okay. So I'm going to open it here, and now it is a blank file. Now I need to start somewhere. Now there is a documentation, the Python, the PyMPC documentation in STKO on our website, so you can look at it. If you don't know how it works, you can start with one of the existing files. For example, this one will be very similar to the ASD embedded node element. So you can go here and you can try to understand the different functions and how they work. Okay, but I will try to explain you step by step. So the first thing that you do in Python is typically to import everything you need. Okay, now in this case, this is PyMPC, which are the functionalities we have inside STKO for Python. So you should always import this one. This one is a module we use for the unit system. This one is another module we use for an easy writing of HTML. And then some functionalities. Okay, these are standard Python Python modules, math for having the math library and the operating system, and a few other stuff that we have in the external solvers for handling the Tcl files. Okay, so the first thing that you do is to create some import. Now, something else, we can create some utility functions. I will tell you later on what they are. Okay, but this one basically is a utility function for printing an error. Okay, in a way that all the errors will be nicely formatted. Like there is an error in ASD constraint equation element at condition ID. Okay, so that the user will be able to understand if there is an error, in which condition it happened, and which element created that kind of error. This one is another utility function to get an attribute from an external object file. If you don't know what is an external object, an X object, you can see on the documentation. Okay, but sometimes it may happen that you put the wrong name, and so the get attribute does not give you any attribute because that X object does not have this attribute. So this one will be known, and in that case, I will raise an exception with a proper format. Okay, so these ones are just utility functions. Now, let me just explain you what is an X object. This one, for example, is one of the X objects. When you are in STKO, let me run this one. As I told you, the X object is everything we use in STKO to connect with OpenSys. For example, if I go here in definition and I add a time series like this one is the X object. Okay, so the X object is a Python file that contains all the necessary stuff for creating the attributes, which are these ones. Okay, now in the case of a linear time series, you have just a couple of attributes, a Boolean for the factor and a floating point number for the factor itself. Okay, and then it contains, so basically the logic for assigning all the attributes inside the X object, and another function for writing based on these values the Tcl file. Okay, so these are the basic functionalities. So the first thing that we need to do is to create a function for filling our window here in STKO in such a way that we will be able to get all these parameters here. For example, the K, the DOF of the constraint node, the DOF and the factors of the retained nodes. Okay. We are not going to create attributes for the node itself because the node will be taken from the mesh. Okay, so directly from the assignment of the condition. Okay, so this kind of function is called make xObject metadata. Okay, so this one is my function. If I put this function here, okay, STKO will find this file and will say, okay, this file here is a file that needs a GUI. Okay, so I will call this function here and I will create a GUI for this new condition. Now, for creating a GUI, everything I need to do is to create a bunch of attributes. Okay. Now what I'm going to do is to copy this one and I will explain you what it does. Okay, so here I just created a variable for storing a URL for the documentation of this new element. Now, this new element is not yet in OpenSys, so there is no documentation, but I'm going to add it soon. So as a placeholder, I applied the URL for the ASDEA embedded node element. And then I placed a to-do, change the URL when the documentation for the constraint equation element will be ready. Okay. Then I have a utility function called MKA, which stands for make attribute, that basically defines an attribute. You know why? Because we are going to create many attributes. Okay, so a lot of these lines will be repeated. Okay, so in programming, it's very convenient when you create utility functions and you call them over and over again to write the least number of lines possible. Okay, so this function takes a couple of parameters, the name of the attribute, which is exactly what you will see here. Okay, let me just create something. So the name of the attribute is this one. The value is this one on the other side. Okay, the description is what you see here, and the group is the parent of the attribute. Okay, so you can organize your attributes in different groups when they are large in numbers. Okay, so you have the name, you have the type, because your attribute can be an integer, can be a string, can be a vector, so it can be many types. You have a group, you have a description, and optionally a default value also. Okay, so everything I do here is to create a new attribute metadata, assign the type, the name, the group, the description. So the description you provide here is just a string, but I place it inside some HTML formatting in such a way that you have the name as the title, which will be in bold, and then in a second paragraph you will have the description, and then in a third paragraph you will have the cross-link for the URL. Okay, so this is just a utility function to avoid repeating this 10, 12 lines every time. Okay, so now we can start creating all the attributes that we need. Okay, so for example, here, the first thing that we want to do, for example, and you have seen these in many STKO components, these are the dimension and the model type. Okay, because for example, when you create this new node, you have to tell OpenSys what is the NDM and NDF for that node. Now, in this case, it was very simple. It was a one dimension problem for all the nodes. But you know that in STKO, you can mix different model types. Okay, so it is necessary to specify. So what I'm going to do here is to create a couple of attributes like this. Okay, so one attribute will be called dimension, which is the name I pass here, the type, which is a string, and the default value will be 3D. And now here I'm just saying that this one is not a plain string that the user can write, but it is actually a list of possible strings. Okay, so the source of the string will be a list, and the source list will be 2D or 3D. What it means is that the user cannot write any kind of string. He can only choose between 2D and 3D. Okay, and the same thing for the model type. Okay, so the model type is always a string. The default value will be U displacement, but you can choose between U displacement, UP, so displacement plus pressure, or UR displacement plus rotation. Okay, so these are basically two attributes that I always use to understand what is the NDM, NDF for your component. Okay, now imagine you have these two variables. The other thing that you need to do is to add attributes to the X object. And you can do it here like this. So the first thing, you create an X object, you give it a name, and you add the attributes. Now, let me do it step by step. So now I only created two attributes, the dimension and the model type. Now I create the X object metadata. I give it a name. It is very important that this name matches the name of the file and matches the name of the OpenSys component, okay? So that the user can see a parallelism between the STKO component and the OpenSys component, okay? So once I'm done with it, I just return this X object metadata, okay? So this one will go inside STKO and will create the user interface for you, okay? So let's do a test now. Now I close STKO, okay? Because when you add a new component, you have to close it. But when you do changes, it is not necessary to close it, okay? So now I'm going to open it again. Now inside this folder, where is it? Here, he will find a new file here, which is called constraint equation element. Okay. Now, as you can see here, I did this change, and this change is inside my file. Okay. Oh, by the way, I forgot to tell you something. Now I'm doing the changes directly in the master branch, but this is actually something that you cannot do, okay? Because you cannot actually write here. So the right step for you, sorry if I tell you, but the first thing you have to do is to go here and create a new branch, okay? The new branch will be called, you give it a name, for example, add new constraint equation element, okay? You create a new branch, and now it will bring the changes I made here, okay? So my new constraint equation element will have this change, while the master does not have anything, okay? So for example, now I go here in MP, I don't have the file anymore, but if I switch to my branch where I'm working with this new constraint equation element, I restore it, and I will see my file here, okay? So this is actually the correct step. You start from the master, you don't do any modification as I did, I made a mistake. You create the current branch and you do the modification here. Once you will be done with this branch, you can do a pull request, okay? So for example, now the first thing that I want to do is I want to publish this branch. Okay, so this is the starting point now. I have my own file, I'm here. Let's try to go to condition and see if I can see it. Constraint. And I can see it here, ASD constraint equation element. I open it, and now as you can see, I only have these two variables, okay? So these two strings, the first one I can choose between 2D and 3D, and the second one I can choose among them, okay? Now, if you want to do a change, for example, I don't have any description here, you can do it, okay? So as you can see now, I don't have any description. I cancel it, and I go back here. And then, for example, for the dimension, I can say description is equal to no description. I save it. I create another file. I don't know if I have to close a sticky or not. Just let me see. No, I have to. Yeah, I have to reload the sticky. Can I go on condition? Constraint MP, constraint equation element. If I go here, I will see my updated version, okay? Now I have to reload STKO every time because I'm working on the developer version. But actually, when you work on the real STKO version, you will not be requested to restart STKO every time. Okay, so now we have only these two attributes. Let's keep on doing some changes. So for example, we need all the other attributes like these ones. So let me copy them. I go here. So we have the dimension, the model type, and all the other attributes we need. For example, the stiffness. The same way, I call the make attribute. I give it a name like K penalty. The type this time will be a scalar. Okay. The description, you can put it here like a penalty stiffness value used to enforce the constraint. And the default value here is 1 to the power of 12, but we will try to change it later on. Okay. If you want, you can also apply a dimension. Now, I'm not going to talk about this because we don't have the concept of dimension inside STKO, but we are working on it. So if you want, you know, this one is a stiffness, so you can give it a dimension like F over L. Now, what else do we need? We need a K for the stiffness. We need the DOF. As I told you, not the node, because the node we are going to take it from the mesh, but we need to tell OpenSys which DOF we want to work with. In this case, we want to work with DOF number 1, for example. Here we have to allow the user choose the DOF. Okay. So I'm going to create another attribute called CDOF, which stands for constraint DOF. It's going to be an attribute of type integer, okay, because it is a number, not a floating point number, and a description that can be the one-based degrees of freedom of the constraint node, okay, and the name can be constraint DOF. Now I do the same for the retained DOF, but as I told you, in this constraint, I can have only one constraint node, but I can have 0 or multiple retained nodes, okay? So I'm going to do the same, but with a vector, okay, a quantity vector, both for the retained DOFs and the factors for the retained DOFs, okay? So we call them retained DOFs, that basically is a list that contains the first DOF, the second DOF, and so on. And then I create another list for the factors, okay? Because I need to specify that the constraint DOF will be a weighted average of something else. So I need the factors, the weights, okay? This list will be basically a collection of the first weight plus the second weight and so on. Okay, once I have these, I simply need to add them in the same way, like X object, metadata, add attribute, K, and so on. I'm going to copy the files here. So I add all of them, and let's see the differences. Okay, so once you design your entire X object, the first thing you have to do is to make sure that it is working as expected. So I create a new file. I go in condition, constraint, MP, constraint equation element. Okay, now you can see all the differences that we made. Okay, so we have the dimension, the model type, the penalty with the default value with the description here, and you can change it. Okay, then you have the constraint DOF. What is the constraint DOF? Is the one base DOF of the constraint node, so it can be either 1 to NDN. Then retained DOFs, it can be a vector. Now we have 0 components, but it can be more than 1. Like for example, we can have 2 retained nodes, and here we can specify the DOFs. And we do the same for the retained factors. Okay. So now we have all the components that we need for getting this data. Okay. Now the next step will be to have a function that is able to take the values that the user puts here and write them inside the TCL file. Okay. So what we did now is just to create the metadata. So it means the structure that the user will go and fill, and then we will take the values from this data and we will write it to the TCL file. Okay. So this other function is used, the other function that is used for that. So this one is the make XObject metadata. Then there are a few other things that I'm going to explain you, but this one is the other function, which is called write TCL for all the files, but for the constraint, it is called right equal NP constraint or SP constraint. They have a different name. Okay, so this one is necessary for writing it. Oh, Raffaele exited. Okay. Raffaele, did you miss something? Because I've seen that you left the room and then you enter again. Can you hear me? Yeah.
Yeah, I'm just having some trouble with the connection. I hope this doesn't.
No, it's not a problem. But I'm seeing that many participants are exiting and entering again. I don't know if it is a problem with Zoom or not. Refa, did you have any problem?
Massimo, is this Zoom recorded or not?
Yeah, on YouTube. Yeah, now we are live on YouTube, so you will be able to watch it again on YouTube.
Thank you. But, it's very useful and very clear.
Massimo, it's very stable on Zoom.
Okay, because I'm seeing that other people are exiting and entering again, so I thought there was a problem with Zoom. Okay, let's go ahead. So I told you that this next function here is used to write a TCL file. Okay, so let's just create this function, and I'm going to put it here. So this function is fine. We created it, we tested it, we are done with it. Okay, so next step, we need to create a function that, for the moment, it does not do anything. It just print hello, for example. Now let's see when this function will be called. Okay, so as you've seen, the first function is called when you create the widget. Okay, so you go here, you create your new constraint. Okay, and here I called this function. Okay, but let's see when this function will be called. Okay, so for example, let's save it. I want to save this file in a folder called test, and I called it test. Okay, so we are here. Let's try to write the TCL file. Okay. Oh, of course, now it will not be called. Why? Because we don't have, this condition is not assigned to anything, and it is not inside any load pattern. So this function will not be called. Okay. But now let's create just a load pattern, a constraint pattern, sorry. So add pattern, constraint pattern. This one is going to be a multi-point constraint because we decided to add it inside the MP. Okay. So this one is going to be a multi-point constraint. We select it. We go here. Now we try to write the file again, and we will see our string here. So this function will be called. Okay. So here, basically, this function will be called every time we try to either run or write the input file. Okay. So basically, here we have to put all the logic we need to write the input file. Okay. And I will try to explain you how it is done. But there are a few other optional functions that we need in this specific example. So the first one is very simple. I don't want to bother you with this function. You can simply copy paste it by other condition. But it is called make condition representation data. It is only used by STKO to decide what kind of representation you want on the user interface. For example, for standard constraint, we use points. Okay. But for forces, for example, we use vectors. Okay, and this is the place where you can decide it. Okay, so you can decide what kind of representation it has, and on what kind of geometries it can be applied. Okay, so in my case, this kind of constraint can be applied only on interaction. Okay, so on interaction is equal to true. And all the others, vertices, edges, faces, and solid will be equal to false. In this way, when I create this interaction, let me show you. If I place this one here and save it, okay, now I reload this file. Okay, now let's try to see what happens. For example, if I create a geometry like an edge, then I create a face, And then I create an interaction between, I can generically, between this and this. Okay. And now I edit the condition and I try to assign it. Okay. As you can see, I cannot select the edge. I cannot select the face. I can only select the interaction. Okay. Because I decided here, this is where I decided that this condition can be applied only on interaction. Okay. So basically, this function is used for deciding the target of the condition and deciding the visual representation. Like I decided points. So if I assign this on this, I go in condition, I will see points here. Okay. So this is the functionality of this function. Now let's move to the other optional function, which is the request nodal spatial dimension. Okay. Now let me copy it and I will explain you the meaning for this function. Once again, this is not mandatory, but sometimes it is necessary, like in this case. As you can see, if I don't have this function, I don't have an error. There is no problem. But no matter what I do, if I do not place that function, the constraint node, okay, if it is free, like in this case, or not actually here, but in this first example, this node does not belong to any element. Okay, so STKO does not have a way to understand what is the number of dimensions and the number of degrees of freedom for this node. So if the only way we have basically is to explain it in the constraint file. Okay, in this way, I tell all the nodes that they can be a certain combination of dimension or model type. Okay, so for example, in this case, this is a very generic constraint. And this constraint can be used in any kind of NDM or NDF. Okay, so what I do is a simple logic here. I first get the X object, I get the dimension, okay, and it can be either 2D or 3D. Now in this case, I want to know if it is a 2D. So I say this variable is equal to get attribute string equal to 2D. What it means is that if the user selected 2D, this one will be evaluated as true. So this variable will be true, otherwise it will be false. Same thing for this other. This one will be true if the user selected UP. This one will be true if the user selected UR. Okay. If both of them are false, it means that the user selected just U. And now what I do is a simple logic to say, okay, if we are in 2D, NDM will be 2. If we are in 3D, NDM will be 3. Then in 2D, if the user selected UP or UR, okay, we have 3 DOFs. So my preferred DOF will go first, and then I will put the other. Okay, so the user prefers 3 DOFs, but this element can work also on 2 DOFs. And the opposite here, the standard way. In 3D, let's do the opposite. So we have 3 dimension. Then if the user selected UP, we have 4 DOFs. So my user-defined request will be 4 DOFs, and then the others, 3 or 6 DOFs. If the user selected UR, I put the 6 DOF first because we want displacement and rotation. But we can also accept only displacement or displacement pressure. And the same thing here. So here the default will be only displacement, but we can accept also displacement pressure and displacement rotation. Okay. So this is a standard way to say STKO if we want a precise couple of NDM or NDF, or if we can allow many of them. Okay, so now imagine your element works only with UR. You can avoid all this logic and you can say NDM is equal to 3, NDF is equal to 6, and you return it here. Okay, so it is not so complicated. Now what I have to do is to create a map, a dictionary actually in Python, where basically for each node, I give it a tuple, where the first component is the NDM, and the second component is a list of all supported NDF that I want for this condition. Okay. Now this condition is actually attached to many interactions. Each interaction can have many elements, and each element can have many nodes. So what I do is a simple loop. So I get the document, I get all the interaction this condition has been assigned to, and then I do for each interaction, I get the mesh associated to this interaction. Then for each element in this mesh, and for each node in this element, I request for this node, this NDM and this NDM. And then I return this map to STKO. With this function, STKO will call this function on every component, and he will be able to understand what is the NDF or NDM for all the nodes in the model. Okay. Okay, so this one is the other function, and then we need to put all the logic for writing the TCL file here. So this one will be the last topic. Now this one is a little bit complicated. I will try to explain you step by step what it is doing. Okay, so the first thing that we do is like something like this. I want to write what is the final command that I want to produce. Okay, this is actually useful for to have a reference. Okay, so this one is what I would like to be able to write. Okay, so the first thing that I'm doing here is to get the X object. Okay, so the input of this function given by STKO is the process info. The process info contains many components. You can see it on the documentation. One of them is the current condition that is being processed. Okay, because when you click on the write input file, STKO will process every component, like every material, every element, and every condition. This one is the current condition. Okay, so the first thing that you do is to get the X object from the condition, which is basically here you have the condition, and this one is the X object. Okay, so this data here. So basically, this function is just getting the X object out of the condition, so that I can get the attributes and understand the values. Next thing, I need to get the document. Okay, this is how you get the document. You have a module called called app inside PyMPC. Okay, so inside PyMPC you have this model called app, which is the STKO application. You can get the KAE document, which is the pre-processing document, or the post document. Now here we are in pre-processing, so we need the KAE document. Now, if there is no document, you need to raise an exception. So you need to throw an error. But this will never happen, actually. This can happen only if you don't have any document, but it means you have a crash or something. Okay, once you have the document, you can get all the interaction in this condition. I go here and I go here. Okay, so just to explain you what I'm doing here, let me print something like how many interactions, and I can print len all interaction. Okay, let me stop here and let's see what happens now. Now if I write the TCL file, here we have an error because we need to mesh it, of course. Okay, and write input file. How many interactions? 1. Why? Because we assign this condition to only one interaction. Now imagine we go back to the geometry, we create another interaction like generic link. Okay, and from here to here, and we attach them with this one. Master and slave, right click. Okay, so we have another interaction. I edit the condition, I assign it to a new interaction. Okay. Now I mesh it again and I write the input file again. Now I should see how many interactions, 2, because it has been assigned to 2 interactions. Okay. So basically this function is getting from the condition the assignment, all the interaction that has been all the interaction this condition has been assigned to. I get them, and then I simply do a quick check. So if I did not assign this interaction to anything, so if the length of this vector is 0, I can simply return. I don't need to go further. Okay. Then we can proceed. basically at this point, we have some interaction, so we need to write something. So here, the first thing that I do is to check, is to get a Boolean value for understanding if I'm working with parallel processing or not. And then I get all the values, okay? So first, this one is very simple. pinfo has a variable called process count. By default, it is equal to 1. If you're doing parallel processing, this variable will be larger than 1. So its partition can be equal to this function. So it will be either true or false based on the process count. And then I need to get the real value the user entered here, like k is equal to this function, get attribute by name. So you say, okay, I want to get the attribute called k penalty out of this X object. This variable, I know it is a quantity scalar, and I can get the value. Here I can get the integer of the constraint of, and here I can get the quantity vector and the associated value and so on. Okay. So what I can do now is to try to print them, like let's say print k, then print cdof, print rdofs, and print rfact. Okay, now let's see what happens, what it means getting these values. So if I'm here and I want to remove this interaction, I don't need it. It's the second one, remove. Okay, mesh with mesh. Now the default values that I have are 3D UR 112. Let's put 3 here. Here I want to put a vector of 3, where I put 1, 2, 3, for example. And here another vector of the same dimension when I put 0.1, 0.2, and 0.3. Okay, now let's see if I can get these values. Okay, write input file. Okay, so what I get here is exactly that. So I get the k, the user entered, the cdof, the rdofs, and the r variable, and the r factors. Okay, so basically this one is the opposite of this one that I created here. Here I'm creating the model and giving the default values. Here instead I'm getting the values the user entered. Okay, so once I get the values, I can start writing them to the file. Now let me go quite fast on this. Well, of course I will do some checks. For example, in this kind of model, as you've seen here, the number of dofs and factors should be the same. Okay, they should be list of the same length. So the first thing that I do is to make sure that the user didn't create any error like this. So this one is a first check. If the two are different, I will see an error here. This exception is what actually happens when you create mistakes in STKO and then a Windows pop up. Like, for example, here, if I go here and I change the number of them. So for example, this one has a length of 3 and this one has a different length of 2. I press OK, and then I write the input file. What I should see, sorry, here the message I have to put. Error and length. What is this? Error and then the ID. Sorry, lm.id. No, it should be the info condition ID. Okay. Okay, do it again. And this is the error that I have. Error in ASD constraint equation element at condition 1. The length of retained of 3 should match the length of retained factor, which is 2. Okay, and then you have the trace back. This error happened in line 151 of the ASD constraint equation element. Let's go and see here 151. Okay, so this is actually an error that I generated to check the input of the user. Okay, so keep in mind that while you're doing these changes, Github is keeping track of the changes that you're doing. Okay, so we are up to here now. Now we'll try to go quite fast. So this is a way to get the data, to get the values. You do some check, and then what I do is something. Let me go first back here, and then explain you what is inside this function. So I first place this. Now we want actually we want this object to work. Let's put that to do here. We want this object to work both in sequential analysis and parallel analysis, okay? So what I do is basically, well, the first thing I encounter this file, I write a description, okay? Because it is nice to have a description inside a STKO file. So I create a description format and then I write it to the pinfo out file. Out file is a pointer to the file, which is the current file STKO is writing to, okay? And then I call a function, okay, based on the parallelism or not. For example, if the model is partition, I do a loop for every process ID in my process count. I set the current process ID pinfo, and then I call an internal function to get with the two parameters, the current process ID and the process block count, which is a variable that this is actually a pretty standard way of doing it, so you can simply copy paste it. Otherwise, you call the internal function with 0 as process ID and no process block count because you will call it only once. And then I need to write this function here, like not here actually, here. This one will be a generic function, like def internal, and then what I need, which is this one actually, a pretty lengthy function. Okay, so basically if we are working in sequential version, this one will be 0 because we are here. The process block count will be 0. But if we are in a parallel version, we have the process ID, so we can skip the elements that are not in that process. So this is the way STKO uses to write STKO file for the partitioned OpenSysMP. Okay, so I'm going to copy everything and I will try to explain you what I'm doing because this one is pretty complicated. So I understand it is quite hard to do for the first time, but you can practice, and this is quite interesting for people that have some basics in Python and they have some programming concept, okay? So it is not very simple to start with, but it's very powerful. Okay, so the internal function, what it does is to reference the variable that I already took here, so all the interaction, and then I do for each interaction, I first check the interaction. So the interaction should be for this kind of element a generic link. Why? Because basically I want to write a single element for all the DOFs involved in the interaction. Okay, so I don't need the node to node link or the node to element, but I need a generic link. So one constrained DOF and many retained node. Okay. So it should be a generic link. If it is not a generic link, I will throw an error. Okay, that's why here I decided to use, what is it? Interaction, generic link. Okay, fine. So first thing we get, we do some checks about, we just do some check. Do some checks about the interaction type. Okay, then this interaction has an associated mesh. Okay, so first of all, we need to get the mesh from the interaction. We get it, and then we need to process each element in this mesh here. Now I wrote a description here. There should be only one element per interaction for a general link, but the loop is more generic for future implementation. So it is not necessary to write this loop because I know that this one is always a factor of 1 because a generic link generates only one element. But you never know, probably in future you can change it. So it's always better to write a loop, okay? So it will work both now and in the future if we try to, I don't know, create more elements for each generic link. Okay, for each element in this list. And here is where I apply the check for the parallel version of not. For example, if I'm working with a parallel analysis and this element is not in the same partition of this process ID, I simply skip it. Okay, so I will not write it inside this file. I will write it later on. Okay, if I pass this check, it means that this element is on the current partition. So I start my logic here. First, I get some information about the nodes. For example, I get all the nodes for this element. An interaction follows always one rule. You can get the number of master nodes and the number of slave nodes, which is equal to the total number of nodes minus the number of master. The master comes first, and then you have all these slave nodes. Okay. So here I do a check. The slave node should be only one, because in this kind of element, you can have only one slave and many retained nodes. So you do another check here. Once I pass this check, I can go on and I can say, okay, now I get the ID of the constraint node. As I told you, in a link, the first nodes are the first NM nodes are masters and the remaining are slaves. So the slave in this case, which is only one, can be only at the end. So I can get it from element nodes -1, because in Python -1 means the last number, dot ID, because this one gives me a node. A node is actually an object that contains the ID or the coordinates. I just want the ID. And then I do the same for the retained nodes. So our nodes will be a list containing lm nodes I dot ID for each I in range node master. Okay, so this one is a simple way in Python to build a list in an inline function. Then I do another consistency check. Now I need to make sure that my mesh has the same number of retained nodes as the number of RDOF or R factor. Okay, so for example, I need to have the same. If here I have 2 nodes, here I need to have also a vector of 2. Okay. Okay, let's go back here. Once this check has passed, I need to go. I need to start writing something. So here, what I'm doing is to open the if statement block for the current processor. Okay, so if I'm working on a partition file, I need to write this one inside an if then else block. For example, if I am on processor 1 or if I am on processor 2 and so on. This one is what basically does this stuff here. So if the STKO variable process ID is equal to the current process ID, I can write it with an if, otherwise with an else if and so on. Now here I'm doing some stuff that I'm not going to explain you. This is not very important. I'm just saying that since it is a condition, you can apply multiple conditions to the same interaction. Okay. Now what happens is that I cannot use the ID, which is this one, LMID, because the LMID is the ID of the interaction, which is only one. But if I apply 2 conditions to the same interaction, I will generate something like this. I will generate 2 lines of code like this one with the same ID. Okay, because it is the idea of the interaction. But this is going to create a problem in OpenSys because I cannot have 2 elements with the same ID. So basically what I'm doing here is to generate on the fly new IDs, okay, that are not overlapping with the existing IDs. Once I've done this, I can finally write the element, okay, which is this one, element, ASD constraint equation element. And I put everything here. So the first thing that I do is I put some indent to have a nice indentation. Then I put the element ID. Here I put the stiffness. Then here I put the constraint node. Here I put the constraint DOF. And here I put the list composed of all the triplets. For example, retain node I, retain DOF I, retain factor I for each I in range master nodes. Okay, then this function is finished. When I call it from here, this will process all the interaction and will write the necessary files. Okay, so if you want to understand basically what it does, once we are done with it, okay, once you're done with your code, you can test it. And here I have a file for this test, which is actually here, test CA element in STKO. You can open it. Okay. Now, if everything is fine, in this kind of example, I created a very, very simple example, similar to the one that I wrote manually. But basically I have one line, which is this one, that goes from node 0 to node 2. This one is at position 0, this one is at 100. And then I created another point here in the middle, okay, point 2. Then I created an interaction. This interaction is of type generic link. The constraint node is this one, while the master nodes are 1 and 2, okay? So this one will be the first master, the second master, and the final slave, okay? Once I've done this, I simply fix the base with all the degree of freedom here at the base. Yeah, I fixed all the degrees of freedom at the base. This one is actually a beam. Then, well, this one is nothing, basically, it can be removed. Then I applied an imposed displacement on the top node of 100 units in X and 100 units in Z, okay? So this is fine. And then what I did is to apply several boundary conditions. Okay, so you can see that this node is placed in the middle. So here what I've done is to create several boundary conditions that connects these nodes and say, okay, this one is my penalty parameter. The model type is 3D. Sorry, the dimension is 3D. The model type is displacement plus rotation. And here I want to constrain the first dov of the constraint node, which is the X displacement. And I want to constrain it with the other two X dovs. And the weighting factor should be 0.5 and 0.5. This one means that displacement in X of the constraint node, so the node in the middle, will be equal to 0.5 times the displacement in X of the first node plus 0.5 times the displacement in X of the second node, okay? Then I basically do the same for all the other degree of freedom, okay? So this one is 2, and I put 2, 2 here, okay? And all the other stuff, I do it basically for all the degrees of freedom. And basically what I'm doing with this approach is to say that each degree of freedom of the constraint node will be the weighted average of the associated degree of freedom of the other nodes. So at the end of the day, when I run this analysis, you will see that this element is moving and this node is following, okay? Now, just to make sure, for example, if I don't use them, let me just fix this node. Okay, so I fix this node in the middle, and I don't use any of this constraint, okay? So what you will see is a beam moving, and this node will be, this node in the middle will stay at its own place, okay? So let's run it. Okay, and let's load the database. I show the nodes and I switch off the beam, okay? So you will see here my beams are from here. This node is completely detached, and of course it is not moving because I removed the connection between them. So if you look from the top, my beam is moving, okay, from 100 on the X and 100 in the Z direction, okay? But this node is not moving. Now I go back here. I remove this fixity. I don't want to fix it anymore. I remove all the fixities, and for each of them, I add these constraints here in the multi-point. I make room for 6 of them. And condition X, Y, Z, Rx, Ry, and Rz. Okay, okay, and then I run the analysis. Oops, I made a mistake here. Where is it? Boundary condition. X is fine. X, Y, and Z. Let me see what I did, because actually this one was working before. I made some change. Oh, first of all, let me see if I wrote everything correctly. No, I didn't save this one. That's why I need to save it, because in fact, if I go here and look at analysis steps, yeah, I didn't wrote anything. Okay, so I basically forgot to save this file, so no constraint has been saved. Now I write it again, just to see the difference. And now you should be able to see this constraint here. So as you can see, I applied 6 of them. The first of them is constraining node 3 at DOF1 to node 1 and node 2 at DOF1. And the same for the other DOFs, okay? And each DOF of node 3 will be the weighted average of the other DOFs of the other nodes, okay? Now, if I run this one, it converges fine. Well, of course, because before there was no constraint. I reload the database, and now you will see that this node is following the other 2 nodes, okay? So basically, this one is the way to add a new component from OpenSys to STKO. And this is the first step that we are going to use with Raffaele for creating this moving train, okay? So this is the first building block that we need. And future webinar, we will keep on working with this, and we will show you new updates, okay? So I understand this one is quite complicated as a webinar, but if you're interested in Python and in how to extend STKO, this is the starting point. So basically here you have seen how to contribute. Oh, of course, and the last thing, okay, once you have done your code, you have all your modifications here, you are sure that your code is working. Now in this case it is working. The last thing that you have to do is to commit the changes that you have done, like in this way, and you push to the origin. Now what you have is that this code is in your current branch, but it is not in my master branch. So what you can do now is to create a pull request. When you create a pull request, it will go on the web page here. Now here you will see your account, and you will see, okay, added. You can add a title, you can add some information. We just added a new component. Now, of course, you need to give all the proper information. You can create a pull request, okay, like this. And then in your case, you will be done with this. So when you create the pull request, you cannot do anything else, okay? So you create the request. Here you have a check saying that your modification has no conflicts with the standard branch. And then you have to wait. We will respond. And if we don't find any mistake, we will simply merge the pull request, okay? So once you do the pull request, you are done. We will contact you on this message board. And if everything is fine, I will simply accept your modification. Now that I've done this, I merge the pull request. So you will see this. When you will go back to your GitHub, you will be notified that your pull request has been accepted. So I can simply delete my branch because there is no need anymore for having this. Now I'm back on my master. On my master, I don't have this file anymore, like this one. So I don't have it here like this. It has been removed because I removed my branch, but now it is on the public branch. So I can simply go here, go to the repository and pull. Pull is basically getting everything from the master. And now if I go here, I have it back, okay? Because you created it on your branch, you made a pull request, I accepted it, and your modification now is in the standard repository. So this one is the basic way of working on GitHub, creating your modification and interacting. Now it is quite complicated, I understand. As I said before, the first thing, if you're interested in extending the STKO library, the first thing that you need to do is to understand how GitHub works, then how the PyMPC library works, which is the extension of STKO to Python. And then you need to start following this webinar and the next webinars we'll be doing in this on this topic. It is quite complicated, but if you are interested in extending the Python in STKO or creating your own automation, this one is the starting point. Okay. So it's all for today's webinars. I don't know if you have questions, but I think you are quite tired because this one I understand is quite complicated. Raffaele asked me for this webinar, but he was having connection issues. So probably he had some questions, but now he's not here anymore. Do you guys have any question? Something that is not clear?
No, Massimo, thank you very much. It was
Okay.
very useful.
Okay, so you can watch. Well, of course, we are on YouTube, so you can watch it over and over again because I understand that I was pretty fast on certain topics. I will share with you by tomorrow or next week all the data that I've done here. But of course, in your case, it will not work because we still have to add this element to OpenSys. We will do it on the next days. Okay, we will add this element to OpenSys. They will pull it on the basic repository, but it's the first place to understand how to use it. Okay. So if there are no questions, thank you for joining this webinar, and see you on the next webinar. The next webinar will be more practical. It will not be on programming. We will do probably a series of parallel webinars on programming, so that people that are interested in this kind of stuff can follow these webinars, and people that are interested in more practical webinars can follow the others. Okay. So thank you for being this webinar, and see you on the next webinar.
Okay, thank you.